Okay, so welcome everybody. So tonight we are starting the 2025 series of meetups. And we're starting with what I anticipate to be kind of 2 weeks of discussion on reinforcement learning with human feedback. Start out with some of the same caveats we've already mentioned. Informal group, look, we invite discussions. In particular, in this one, it's not an area that I'm an expertise in. It's an area I just kind of signed up to review and lead the discussion. And so there's a lot of things that are sketchy for me. Feel free to jump in with corrections if I've made an error, or if you'd like to add additional discussion on it or ideas around it, please feel free to do that. And then I'll also make a plug that if you have an area that you're interested in, signing up to lead a discussion is a great way to learn more about it, because it really kind of puts you in the mode of trying to understand it, simplify it, to present it. So I open that up and invite other people for other topics. Okay, so let me, with that, share my. So originally started out, the discussion on reinforcement learning with human feedback. And this is the agenda that I kind of came up with. So do a little bit of background on reinforcement learning. So that's something this group has gone through a number of times. It's been a while though. And so I went back and did a little refresher for myself, and there was quite a bit there I was struggling to remember. So maybe some of the other in the group can help me out with that. Then we'll do the RLHF, kind of track down what that meant and where it came from. So there's a number of papers that we can kind of wrap in a bit on that. And then I'm anticipating this goes out to next week, which is introduction to direct preference optimization, which was a follow-on way to optimize language models based on human preferences. I think it was Ted identified a document here that did a broad survey of different reinforcement learning techniques. So we can dive through that if we have time. I think we probably will. If I've prepared up to about intro to DPO right now. And so if we get that far, I think we probably will have enough time to get through the rest next week. Okay, so here's some links to papers, and I will post this. Let's see, I can probably post it on, I should have shared this on the Slack. I'll share it anyhow at the end of the meetup if people want to go through it. But the links for the three papers I initially was targeting for those three topics I just mentioned. So RLHF, this one is the document. Let's see, reinforcement for human. I think that's, move this down. Yeah, okay. So I take that back. I thought I had referenced the RLHF one. So this is actually the one that kind of more covers the core architecture behind the RLHF. There is another document that we'll also include, which is around the Instruct GPT, which is the one that actually popularized the term RLHF, or reinforcement learning through human feedback. So we'll kind of put those in position as we go. And the direct preference optimization DPO, that link here, and then the survey, if we get to it, is linked there. Do you guys want me to stop and post the link to share the presentation, or can we do that at the end? Any preference?
You can share it now, Roger.
Share it now? Okay, let me see. How do I do that from here, I wonder? This might take a little longer than we really want.
You could also put it in the Zoom chat for now if you want.
I think I have to share it in order to let people see it, even if I put it in the.
There's a big blue share pill in the upper right.
The,
Yeah.
the upper right, yeah.
There you go.
Okay. I'll put that in Slack.
Awesome.
Thanks, Roger.
Mhm.
Oh, while Roger's putting that in here, this is our Slack channel. If you see the West Coast machine learning there, if you are interested, just join us and we'll turn you on it and what have you not. So
Yeah, if you can, there's a link, Jerry, you can share a link that people can follow to join if you want to.
yeah. Let me just-
Okay, so those will be, the whole document should be there, and then afterwards, I'll add it to our GitHub. So we have a GitHub repository, the Slack channel, and then the YouTube channel. But I'll post the document probably after the 2 weeks. I'll post it, take it from Google Doc, and put it into the GitHub. Okay, here's some sites that I ran across as I was researching. So the first one was on Hugging Face. So they have a, let's see if we can do that. Illustrated, oh, I already had it up there. Illustrated reinforcement learning from human feedback. This was a pretty good one. And you'll see some of the slides I've taken some of the graphics from. The other one, welcome to spinning up in Deep RL. This is a pretty good one from OpenAI. It goes through and talks about an introduction to RL, different ideas, concepts in RL, including policy optimization. And they also have some code, I think, in here, running experiments, et cetera. So it was a helpful site. If you're interested in RL, it's a good place to go, I think. Here's one on policy gradients, another site that I found. I will actually jump over to this one, I think, at one point when we're talking about what are the equations associated with RL and PPO. And then this one, Letitia AI Coffee Break, she had a good positioning of DPO relative to RLHF. So I'll go to that video at some point too, when we get to DPO. Okay, so starting then just kind of, I don't know how brief this will be, but a brief introduction to reinforcement learning. And again, we've covered this before. I probably will make some mistakes here, and again, jump in if you catch something. So the first part of it is we start with an environment. So an environment has something that has state internally. It's typically a Markov decision process. And that is, we can read it here as Markov process is a stochastic process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So it's deterministic, not deterministic, I take that back, but it follows a sequence of states. There's the link to it, just if you want to look it up on Wikipedia. So the state is defined as a complete description of the state of the environment, but an observation is either a full or partial description of the state. And it may not have all information, and it could have very little information. So a state, it could be, well, I'm not sure I can come up real quick with an example of something. Fully observable would be something like the inverted pendulum, where you can measure both the angular velocity as well as the angular position. Example of fully observable. Maybe that we had one that you only measured velocity, you couldn't measure position. That might be an example of a partially example one. In the state, transitions may be either stochastic or deterministic. So when you take an action that causes you to transition to the next state, sometimes if you're in a given state, you give it a specific action, it will always get to the same state. Other times it's more of a probability distribution over states. So it might take you to the place you expected, the higher probability place, but it might also take you someplace else. And then action and state spaces are both. They can either be continuous or discrete. So some of the early examples I remember having kind of if it was kind of a maze, how do you get from here to here without falling into a hole, et cetera, trying to get to your goal. We did some few learning examples I can remember. I couldn't find the slides exactly for that, but where the state was, discrete, one of 16 positions or something like that. And the action was, go up, go right, go left, go down type of thing, would be examples of discrete actions. The other one I gave, the inverted pendulum, is an example of continuous action and state space. Key thing is the environments are non-differentiable, so you can't like propagate a loss function through the environment. So you end up doing something that kind of becomes a proxy, trying to approximate the state that may be internal in a way that is differentiable. So that's part of the process. Anything to add to that? Yeah, Dave. Dave, go ahead.
Well, just a question about this. You mentioned about pendulum being one of the examples. So if you have the velocity and the position, then it is deterministic, or is it probabilistic after that?
I would say that's kind of deterministic, just because the laws of nature are pretty predictable. But you might say that the measurement of the velocity could be noisy. So at least the observation could be stochastic. The action likewise could be noisy. So it probably is a good example of a deterministic one. But I would guess that measurement noises and stuff like that also make it a little bit stochastic. Does that make sense?
Yes. And then your second example where only one of the variables is visible, then that definitely makes it, then you have to guess on the other variable.
Right.
If only speed or if only position was visible, then somehow you have to guess this velocity and other things.
Right. Okay. Anything more? Or is that good? Okay. So in these environments, you have state transitions. So you actually get an initial state that doesn't fit in this picture very well, but you'd get an initial state. You could take an action based on the initial state. So those are the starting states. You take an action when it's in the starting state, and you get in return, you get a new state. So it transitions to a new state, and you will get some sort of reward. The reward is key. That's fundamental to reinforcement learning, is a scalar reward value. I just wanted to point out here that the environment, the reward could come from the environment. So like alpha 0 or something like that, where you're playing a game and you get a reward that says, yeah, you win. That would be a reward from the environment. Or it could be something external. So if you have something like a pendulum, we might, a reward might be something we code based on the measured state. So we want the state to be the pendulum is upside down, pointing up, and that's what we consider a reward. And so we just add the reward based on an observation of the state. Either one of those two works. But always, in all cases, it's a scalar and finite value.
Could that be something, Roger, like in a game? Let's say we had football, soccer, whatever you want to call it, and the ball rolls through the goal, then the extrinsic reward is like another point or something like that.
Right. And yeah, that might, I guess in many ways, that would still be, it's got to be a scalar value. So somehow you got to convert, point scored needs to come out as a reward. Scalar value out. Yeah, Ted, did you have a comment?
Oh no, I'm sorry.
You're joining
I will say though that you and I may think of it as extrinsic, but from a theoretical modeling perspective, the reward comes from the environment.
Yeah, yeah,
You think of it as that.
yeah. I agree. When I was thinking about environments where we were kind of adding it on, and we'll see that when we do RLHF, but uh, conceptually, yeah, it's what we call the environment is both the state transitions, and the rewards that we get out of it. Okay, and then so the goal of reinforcement learning generally is to find a policy that maximizes the reward over a finite or infinite time horizon, and pointing out that the reward may be very sparse or very noisy. So chess is an example of sparse, that you play a long time, or some people, I take longer than most, but you play for some period of time and you don't get a reward. That -1 doesn't come till the end. So, okay. Reinforcing that. So one of the things that I remember when we were doing RL that I was playing around with, we played around with, was the AI gym. It's been handed off. It's now called Gymnasium. But it is a simple programming environment that allows you to play with different RL environments. So it models all the different things, and they have things like inverted pendulum. I think they have a cart. I can remember a cart in a well, and a number of different things. It follows a real simple flow, which is you start with your initial state sampled from this, the space of starting states. That's what the reset does. And you get your first observation, and then you can sample in one fashion or another from the action space. So this particular sampling is just a random sampling. Sample from all the possible actions, and depending on the environment, that I guess could be discrete or it could be continuous. Likewise, the observation could be discrete values or continuous values, meaning a member of the real numbers. You take your action and you take the environment and do step, means let's transition to the next state, and it returns an observation of the next state. Again, may be fully observable or partially observable, and a reward. These other things are more kind of housekeeping things that we don't need to worry about too much, but you guys can see my cursor, right? Can you? Yeah, okay. Anyhow, so that's the state that I observe, and then I can continue looping on that. So real simple, get the initial state, sample in action, do a step, and you get your next observation and reward. And so you can play around and create, test all your different reinforcement learning training algorithms using something simple like as that. But it kind of reinforces that this is the definition of RL. Okay? Any questions so far?
Hey, Roger, just one clarification. I think you said the word policy, but you didn't necessarily define it. So the policy is, yeah.
Yeah, okay.
So the policy is the rules for what action you take when.
Yep. And I'm not actually sure, Ted, is the action a distribution over the actions, or is it sampled? This was something that came later.
So, well, the problem is that RL, the desire is for RL to be able to cover as many situations as possible. There's some people who think that RL covers all of machine learning, right? But so there's always, it could be this or it could be that. It could be this or it could be that. That's largely because if it wasn't able to support it, then they tried to extend it so that it could support. Okay. So the bottom line is in a game like chess, you can get away with possibly having a deterministic policy where you say when the board looks like this and it's white's turn to move and I'm white, then I'm going to always do this. I'm going to move my bishop from here to there. Okay. In a game like rock, paper, scissors, you cannot be successful with a deterministic policy. You have to have a policy that has randomness in it, or else you will be crushed by your opponent once they've observed your style of play for a little while. And so in that case, your policy explicitly says, roll some dice. 50% chance that I'm going to do this, a 50% chance I'm going to do that. So it's still the rules for deciding what action you take, but your rule includes rolling dice.
Okay. So when it is past the environment, in the gymnasium stuff, you've actually, I guess, already sampled it. So in some ways answered my question there. In general, when we get down to the RLHF, I have a question about how that works if the environment, if we should think of it as the distribution or the sampled action space.
Yeah, so this example is meant to be a hello world, very simple example, but where you have that line in the middle that says action equals and then, sample.
Yeah.
Okay. Normally what you would say is look up my state from all possible states in the environment and use the policy to tell me what action to take based on the current state.
Yep.
And again, the rule could say roll dice and do one of three things, but nevertheless, it's going to have a very specific hard-coded rule, whether that rule involves randomness or whether that rule is just 100% do this.
Yeah.
Okay. So we just don't see that here in this sort of hello world example.
In terms of how
yes.
the action is
yes.
determined.
So there's the rewards and the whatever that are involved in training and choosing really good rules, choosing a really good policy. But once you're playing the game or doing whatever, running the robot with RL, then really all you have is just the environment, the policy, and the action. And once you choose an action, the environment will dump you in a new state. And the reward at that point is irrelevant because you're not training,
right.
so to speak, right? And then you're going to choose another action based on your policy.
Yeah. When we get down to the RLHF, I'll bring this up again because I think I might have drawn it incorrectly. So, okay. I found this.
Just one comment on the reward in there as well. Ted, do you want to clarify on that as well, how that plays in the policy, the reward? Like there are SARSA and some other methods, right? Which include the reward also, I thought.
So the definition of RL as a framework is that you want to maximize your rewards, the sum of all your rewards, over the long haul. And that's a very difficult problem. If I just said to you, maximize your rewards in the next one step, oftentimes that's easily solvable. But so like, in a chess game, it's like, well, what's the best piece you could capture at this point? That would be like the one move reward. But no, what you're trying to do is win the game. And sometimes just taking that other piece means you're going to lose a bunch of pieces. You're going to lose the game. So that's the framework. And then, for today, we probably don't want to get into too many details about the different algorithms and whatnot.
Yeah, we'll hopefully have time for that at the end of next week. Okay, so I was going to just kind of zoom through here again at this OpenAI spinning up, just to introduce the concepts because I thought they did actually better. I found myself cutting and pasting so much, I decided let's just go through. So this is the picture that they use, again, agent environment. So this is policy is what I call that, but they have an action space at time t, and you get a reward state and reward out of that. So that's the loop that we're trying to optimize. These are the things we're going to talk about. So state is a complete description of the world/environment. Observation is a partial or complete description of the state. Okay, states and observations, real valued vector, matrix, higher order tensor, yeah, blah, blah, blah. Action spaces are all the possible actions. Sometimes in games they're discrete, Other ones, like robots, they're continuous. And then the policies can either be here we're a deterministic policy. They use a mu to denote that, or stochastic, and they use pi to represent that state. So given a particular state, I'm not sure what this notation, the dot pipe st is, but the policy is a stochastic policy, meaning you don't know what action it's going to be at a given state. It could be different. For what we're doing, the deep RL, all parameterized. I've seen theta or phi. Is that phi? I think that's phi. As the name of the parameter space. Let's see, what were some other things? Log likelihood. I think they went into trajectory was a concept to introduce. So trajectories are states and actions that we invoked at that state. So this is a particular trajectory that you might walk. And then here they had, I hadn't seen this term before, start state distribution. They represent, I guess that's rho. 0 is all the possible starting states. Sometimes that can be all of it, all of the space. Sometimes it can be a very limited one. So if you look at the inverted pendulum, maybe that can start in all cases, but if you look at a maze, walking through a maze, typically that always starts at the same spot. So the start space is just one cell. But you can sample from that anyhow. And then state transitions, given a particular state, if you give an action, what's the next state? That's deterministic. Or the notation using here is the probability of transition to a particular state is the function of the current state in the action, but it's stochastic. Rewards are based on, so I hadn't noticed this, that the rewards I've usually thought of are related to the state and the action, but they actually throw in all three. So the state and the action and where you ended up. I guess this probably accounts for stochastic state transitions. Because maybe you say, I want to do this, and you think you're going to end up over on A, but you end up on B instead, and B turns out to be really good or really bad. So that's interesting nomenclature I hadn't seen. And then the reward associated with the trajectory is just the sum. If it's a finite horizon, you can just do a sum through time t of all the rewards along that trajectory. In a infinite horizon, they just go infinity, but you generally, how do you deal with this infinite sum? So generally it's a weighted value. So you weight more heavily rewards that you get early and less weight on rewards that you get later on. Okay, and then here, so we're looking for the probability of a particular trajectory, tau, giving a particular policy, pi. And so that is related to, okay, what's the distribution of the initial states? And then the product for 0 to t minus 1 of the probability let's see, I don't know what's the best way to read this. The probability of picking a particular action at that state through the policy pi times the probability of moving to a particular state in response to that action. So it's how likely are you to choose that action, and then how likely are you to end up in this other state if you did choose that action. And then you do that for the entire trajectory. And the expected return, so this is the expected return for a particular policy. Looks like it's just the product of those for all overall policies. Okay, and what we're trying to do, so you'll see that notation.
Overall trajectories, I think.
Here, yeah, overall trajectories, the product of the reward for that trajectory and the probability of following that trajectory under the policy pi. Does that make sense? Okay.
Mhm.
So you'll see this notation, pi star is the optimal policy. So that's the policy that will maximize this J of pi. So the largest expected return over all trajectories, well, all trajectories weighted by their probability under the policy pi. That's called the optimal policy. Some other things that we run in along the way are value functions. So a value function, on policy value function is basically saying, so this is a value function pi under the policy pi for a given state. So what you're trying to do here is say, for any given state, if I'm going to make action decisions from this state based on a particular policy pi, what's the expected reward for the trajectory that I expect, essentially. So that's the value function. There's another one that we see. This is the Q learning that we talked about. So this is slightly different in that I believe Q takes also an initial state, but rather than considering all actions from that state under the distribution that pi would generate for that state, you're instead looking at it for just one particular action. So you're kind of looking, okay, these are all the things that might happen. What if I go down just this one path? And then after the first step, I'll follow the policy pi from then on. And that's called the Q function. Go ahead, Dave.
So Vs and the previous equation right above that, Js, right above, yeah. J pi, sorry. So the only difference is the initial state, if I'm not mistaken, right? So J pi is overall return, and V pi is overall return constrained on starting state equals S, and Q pi is overall return, or not overall, my bad, expected return, conditioned on both the initial state and the initial action.
Yeah, I think that's probably a good way to say it. Yep. It narrows in. Yep.
Yeah, so on that point, what we're trying to do is find a really good policy, and so then the overall returns, the sum of those rewards, will give you the biggest J. That's what you want. But when you're actually, and we're not going to need all of this theory to understand RLHF, but this is like broader context to understand RL in general. When you're dealing with learning and you're dealing with things, you may find yourself in the middle of doing something, in the middle of a chess game or whatever, right? And so Jay tells you if this is your chess strategy, what you're going to do in every possible situation, then this is what your average win rate is going to be. That J will not tell you anything about what you should do in this particular board position halfway through the game. Whereas your V function, because it's for all states, not just for the starting state, then it becomes relevant for saying, oh, if I move my piece and wind up in this new state, is that a good state to wind up in? Or is that a winning state, or is that a losing state?
Right. Okay, 3 and 4. I think these are the exact same thing, except they're the optimal policy. So the best you can do was V star and Q star when pi is the optimal policy. I think that's
And they are equivalent of the previous section's last equation also. So if you just go a little up, right there. So pi star is the argmax for J,
Yep.
and V star is argmax for V, and Q star is argmax for Q.
Yep. Correct. Okay. Let's see. Anything else? Bellman was one that I vaguely remember. So the Bellman equation basically is that the value. So this is looking at the value at a particular state as being a weighted. Let's see how they're doing it. So there's this kind of series. So if I look at my state, the value of my state, it is whatever, if I take an action and I get a reward and land in the next state, my value should be the value of the state that I land on plus the reward. And I think that's what this is saying. That reward, if I'm in state S and I take a plus a weighted value under this policy pi of the state that I land on. It says S.
At an average, basically. So that's why you're sorry to interject, Roger.
Yeah, no,
Uh,
please.
So it is basically, S star is from the distribution. So expected would means there is an integral for all possible next states. So for all possible next states and for all possible actions, you get a reward. First of all, for the current state and action, you get a reward. And based on that, there is a probability of landing in the next state. So there is a gamma of multiplier. So you have a
That's
reward.
Yeah, they call that the discount factor. Is what I'm
Discount.
looking for. So a discounted future value.
That's correct. So you land in some state S prime with some probability, which is also and I'm forgetting the term. When you have this tilde sign, what's the exact mathematical term you
Sampled from, I believe.
sampled from? Thank you. So S prime sampled from P, but then because it's expected, then this is like a double integral here on A and S prime. And in some ways, it's actually a nested integral because for each action, you could have multiple S prime depending on, there's a probability for each RSA also is a probabilistic distribution. So it's a very complex equation, but simplified written like this.
So Roger,
And
oh, go ahead and finish.
No, just going to say like the just the same what you were saying, but just another way to look at it mathematically.
Yeah, no, thank you. Yeah, Ted.
So Roger, I don't know how much you want to go into this like RL stuff because we don't need all of it to get to RLHF. But what I will say about these two equations that are currently on the center of your screen, the way I think about it is by writing our value function, either V or Q, in a somewhat recursive form, where we're writing it as a function of the next state that I'm going to be in for the V function, or the next state in action that I'm going to take for the Q function. By having it in this recursive formulation, that actually makes it amenable to various approaches for estimating these functions. So it'll be very convenient for dynamic programming and for other kinds of things. And that's why we want these Bellman equations. They're no better than the ones we had above. It's just the ones above don't help you do estimation.
It's one of the methods for estimation. I think didn't they in alpha, that alpha series, didn't they use a combination? They had kind of a Bellman equation. No, they did a Monte Carlo out to a certain point, and then I think they used Bellman equation from then on.
Fundamentally, the idea is that if you have a preliminary estimate of all of the values, whether they be V's or Q's, and you take one or more steps and you get actual rewards, you can see how much you differ from what you were predicting at that point. And you can use that to slightly do an update against your estimates. So most of us are probably familiar with gradient descent, where you do a slight update based on the signal that you're getting back. So if your actual is a little higher than what you were previously estimating, you might bump up your old estimate. And if it's lower than the reverse, and this over time will cause your estimates to jiggle and then hopefully converge on something. So for a small problem, you can actually converge on like exact, for like simple games, like, I don't know, tic-tac-toe is probably not too simple, but something that's slightly, bigger than that, you can you can use these algorithms to derive exact probabilities. If I do this and wind up in this state and my opponent is smart, then I have a 17% chance of winning from here.
Right. Okay, and then the other one we'll run into is advantage function. And the advantage function, it's basically the way I read this. So the advantage, again, advantage has to be under a policy. So advantage under policy pi at a given state for a given action is going to be equal to this. So the way I read this is going to be the expected return for the trajectory following policy pi if I take this particular action at my state, current state. And I want to know if that is, I'm going to compare that or subtract out the average based on the distribution of actions from pi at this state. So it's kind of like, is that action better than what you normally would do under the policy pi? And the advantage one is something you'll see, and we're going to end up in something called PPO, and advantage function comes up in there. So that's kind of the concept of what it is. For me, it's a little easier to conceptualize what it is by describing it, but this is the formal math representation of it. And even though they don't necessarily compute Q, it's conceptually the same as Q in PPO.
Can I make a comment about
Yeah,
this?
absolutely.
So when I first heard about advantage, I was kind of confused because there's not really anything new happening here. So like what exactly are you guys talking about? Okay. So the analogy that I have now is if you guys are familiar with the way diffusion models work, okay, and I'm going to use the not the score function interpretation, but just the noise interpretation, right? You take an image, you add a bunch of Gaussian noise until you have nothing but just Gaussian snow, okay? And you train a model to predict how to undo adding the noise and reverse that process. When they actually build those things, the very first thing they did was they said, well, let me predict what the image looks like with a little bit less Gaussian noise. And it turns out that just from a numerical stability, variance, whatever, it turned out that it was better to predict the noise than to predict the image that you got after you removed the noise. In one sense, they're mathematically equivalent. You know your starting point. If you predict one, you just subtract, you get the other. But it turns out that you're better off predicting the noise. This advantage is just the delta between one particular action and, like you said, the average of all of them. But it turns out that in certain algorithms, you're better off predicting that than predicting the Q or the V. In the same way that in the diffusion model, you're better off predicting the delta, the noise, the delta between steps, rather than actually predicting the previous step. So predicting the previous step would be predicting your previous Q or V. And here we're not. We're predicting the difference between the two. And they wanted to give that difference a name, so they called it advantage. That's kind of the way I think of it. It's not really a new independent concept. If you knew your before and after values, you can calculate the advantage. But it's just shorthand for them instead of having to constantly say subtract the two, the delta, the whatever. They named it and they said the advantage. And so you'll see certain algorithms, again, they predict the advantage or they utilize the advantage instead of utilizing the value function.
Yeah, I also tend, it kind of confuses me. It still does a little bit that, why is it better to separate it out advantage and value and Q from the action policy? Why can't it all be in the same place? But as I understand it, it is like there's a difference in the way that you train the two functions, the two distributions. And there's a difference in the variance and the bias of the two. And I can never keep it straight, which is higher bias, which is higher variance, but
yeah, so again, I don't know how much we want to, get into just the basic RL stuff, but the way I think of it, oversimplistically, all of RL, okay, is really about that we have For a lot of these algorithms, we have theory that says that if you run this infinitely, it will converge to the optimal policy. Okay. The problem is if you have a lousy algorithm and you want it to learn how to play chess, then on your cluster of 100,000 H100s, it'll take longer than the life of the universe for it to converge. Okay. So what people care about once we get past the initial theory is, oh, the theory says it will converge. Now what we want to know is how fast it'll converge. Okay. We want an algorithm that practically converges very fast. And generally speaking, variance is the biggest enemy of convergence. So if you just like flip a coin and you look at the values of the number of heads, it'll always average 0, but over time you can get larger and larger swings as you just count up your heads and tails. And so the same that's probably not necessarily a mathematically correct analogy, but that's like how I have a good mental intuition on it. So all of these algorithms are, in general, are guaranteed theoretically to converge over infinite time, but you want as little variance as possible so that you hone in on the signal very quickly.
Okay. Neha, hold your hand just for 1 second. I want to pose one question. So Ted, which has higher variance, the advantage?
The advantage in certain situations will have lower variance because if you have an unknown value and you have an for your current state and you have an unknown value for the next state, oftentimes the unknowniness of those two are highly correlated.
Okay.
So when you subtract, you're actually left with fewer unknowns.
Okay. So advantage has lower variance. The value then has lower bias.
I don't care about the bias.
Oh, okay.
Okay.
All right.
It comes up occasionally, but generally speaking, you're going to deal with an algorithm that has fairly minimal bias because the bigger the bias, you're going to wind up with not the true optimal algorithm policy, but rather slightly off from it because of your bias. So for me, I could be totally wrong here. I'm not like an expert, on RL, but I find that variance is the key thing that you're trying to minimize.
Okay. Neha, you had a question or comment?
Yeah, so is the logic behind residual connections and like residual neural networks also similar in the sense like the difference is easier to learn from like the previous layer to the next one rather than like trying to map it again? Or is it like completely different and I'm like totally off the road?
I would say I think it is something different.
Okay.
The residual streams typically, or residual connections, the way I understand, one is they tend to be thought of as a gradient highway that you can pass gradient down deeper into the network. And the other way to think about it is that it has the weights, the activations tend to be smaller. And so the gradient into the parameters tends to be smaller and not explode.
Got it.
But it's different. It's different than this, I think.
Got it.
Okay.
If I could just say, I think it's a great question, and somebody way smarter than us may be able to give a deeper answer. It's certainly got its parallels, its analogousness. And so, yes, I think you have the right intuition if you think that those situations are somewhat analogous.
Got it.
But as Roger said, it's probably not literally the same principle.
Right.
But yes.
Okay, unless there's any other questions, then I'll go back to the slide deck. So one of the other things I wanted to talk, or one of the key concepts for RL is whether it's model-based or model-free. And some of the earlier ones that we looked at, so like AlphaZero was one that was one where they had a series of AlphaGo, blah, blah, that learned how to play chess by playing against itself. They had a model internal in terms of how the state transitions work. In other cases, you can learn what the state transition is. And then once you know what the state transition function is, then you can do a lot of offline policy optimization. So those are two, those don't tend to be as popular. We don't talk about them as much. The Q model-free Q value learning is one that I remember again, when we were doing RL in this group, we started with this as best I can remember. And that's where we compute this Q, and then you use that to find the optimal. You basically look for the optimal Q and do choose the maximum Q at each state, basically. The stuff that we're going to talk about that applies to RLHF is more around policy optimization. So in the vanilla policy gradient, you would just simply learn whatever your loss function would be on the reward. You would learn the policy directly. One of the ones that architecture that is fairly common is this thing called actor-critic, or advantage actor-critic is a follow-on to that as well. And that's where we have the policy and a value function using those two things we just talked about before, that the value function kind of represents what is the value under this policy from the state onto termination or in a discounted future. In this model, when you have an actor and a critic, you have a policy that creates actions, takes a state and selects an action, and then a critic that is looking at the state and the reward that you got out of it, and trying to predict, was that a good move relative to the other actions that you might have selected. So it's a value-based network typically in here. It's also, I think, tends to look at it's a function of the full trajectory, whereas the policy typically is a function of just the current state. Okay, and then PPO, which is the one that the RLHF paper and subsequent papers used for optimizing the policy. It is also an actor critic, but it does something different in the way that it does updates. So they added kind of some tweaking to it. And they essentially make sure they clip the changes so that it doesn't deviate too much from the original. So here we're still not really talking about language. We're still talking about generic RL. But the same thing applies, is you don't want to make too big of changes to your policy because you can, it becomes unstable, I guess, is the easiest way to say it, if you do that. And the PPO has a way to kind of control that. I didn't quite understand the difference. There's a TRPO, trust region policy optimization versus proximal policy optimization, but PPO seems to be the one that kind of has won the popularity contest. So, okay. So here we go. Actor critic combines the benefits of both the value-based, the Q learning, and policy-based. Lower variance in policy updates compared to pure, since the critic provides a more stable value estimate than Monte Carlo returned. So this would be, this is just, I guess, another approximation for the value function. So lower variance, I'm guessing then that the question is that value function is going to be a lower variance. It's more sample efficient than pure value-based methods, since the actor directly learns the policy rather than deriving its value from estimates. That I didn't quite understand why that's the case, but I guess it makes more sense. You're just learning the policy directly, or it's intuitive at least.
So Roger, if we were playing chess, okay, and you're like, from this position, should I move my knight? Okay. If I said to you, okay, you know nothing about chess, but what we're going to do is we're going to simulate 1,000 ways the rest of the game could look if you move your knight there.
Mhm.
Okay. Versus if I said to you, you have a value function and you know what's a good board position, what's a bad board position, and now start simulating games from after you move your knight. And in the first 10 of them, you lose your queen immediately in one move.
Right.
You don't need to play out all that other stuff to realize, holy cow, unless this is like some master brilliant queen sacrifice, I'm in deep trouble here. Right. So that's why having a value function can be a lot more sample efficient and lower variance because um, you're keeping track of things. So what it doesn't say here is that this actor critic is going to require more memory
Yeah.
because it has to also keep track of a value function in addition to doing the policy rollouts. Okay.
Yeah.
So there always has to be some catch. Well, like, so if this is all better, like what's the catch? The catch is you have to expend a bunch of memory or compute to learning that. But that's why these tend to do better is, and again, it's all about this reducing the variance so that you converge faster.
Yeah. Yeah. I guess I can see that. Okay, so the critic helps guide the actor's policy updates, blah, 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 blah. Yeah, and the main trade-off is this complexity, complexity implementation compared to just a simple policy. Let's see. I was trying to get, so trying to get the math, the loss functions for these guys, and it took a while. I'm not sure that I don't have a real confident feel about this, but the loss function for the critic is pretty simple because you're just trying to, so this is kind of the Bellman equation, the expectation of the essentially, is this a good move, I think? Oh, no, sorry, does my estimate match the actual value? It's kind of a mean squared error fit to the actual value curve. And so that's pretty simple and straightforward if you know what the trajectories are, or if you use the Bellman approach to get there. And then the loss function for this value function then is used to compute the advantage function expressed through Q, that Q minus V, but the advantage function now tells you, is it better to pick one path over another, one trajectory over another, times the probability of picking that path. So A of T should really have been, should also have a function of A and S, I believe, to know what action at what state. And then the expected value of the log of that product.
Yeah, that is captured, I think, in the T subscript.
T subscript.
So I think so, because then that's the probability that they're multiplying for the policy, AT given ST.
Right.
Which is kind of weird because, yeah, no, which is fine, right? So at any time T, in your trajectory for all trajectories, you have an action AT, which can be, I mean, I think AT and ST subscripts could have been different as well. I don't know. So I have to
I've seen
think
it
through a
a
little bit.
couple, I think I saw it a couple different ways, but
Yeah, you have to look at the paper this is actually coming from, but if you're calculating this like update after you've already taken an action at time step t and you're now sitting at time step t plus 1, you don't really need to subscript it. You just know that a particular action was taken at time step t. So that's so
I
you
see.
could say sub whatever, S comma A. Or you
Yeah.
could say sub T, because at time T, we already wrote
Yeah.
down this is what you did from what state.
Yeah, I see what you're saying. Yep.
Yeah. And so the top equation, right, it's how much was my estimate of the value off? Okay. And the bottom equation is actually the same thing. It's how much was my estimate of the value off? Because let's assume you have a stochastic policy. Okay. So half the time you take action 1, half the time you take action 2. If your advantage is positive for taking action 1, it means that action 1's better than action 2, because doing action 1 was better than the average of 1 and 2. So you should ultimately push the policy towards do 1 all the time.
Mhm.
Does that make sense? So your existing policy is 50-50, and it has an implicit value which is needed in order to calculate the advantage, because the advantage is the difference between action 1 and 50-50 split. And the advantage for action 2 is the difference between always taking action 2 versus 50-50 split. So if you started out with just 2 options and a 50-50 split, they'll be opposite signs to each other. Now, you might actually have continuous, and you might have a gazillion different actions. But that's the general gist here is, if you have a positive advantage, it means that doing this was better than whatever mix you currently had. So you should bump up the probability of doing this.
Yep. Yep.
And then in some things like poker or rock, paper, scissors, you will never actually bump up all the way to 100% on anything, because you actually need uncertainty to fool your opponent. Okay. But so just because you're bumping up doesn't mean you'll always bump all the way to 100%. So in rock, paper, scissors, you're never gonna like go above whatever 33%.
The key thing, though, is that the critic is trained on predicting the rewards along this trajectory, stepwise, and the actor then is the signal it gets is from that value function, learning from that value function what's the right selection to make, and so that's where that stabilizes this guy. Okay. I think we already did this. This is the Bellman equation, where it's the value at x0 is the value of a function if you take a particular action at that state plus the discounted value of the state that you arrived at, as indicated by this transition matrix. I don't think I'm going to go into this anymore. And PPO loss function, it looks a little bit more complicated. CLIP is the one they use. There was one that used, I think it was KL divergence, and in the papers they use CLIP, so I just copied that one up there. But it's basically the same thing, except they two things. They use the advantage, which is what we saw before. So interesting that it's the advantage of the policy under the starting parameters. So theta k is the initial kind of reference model. And then it looks at the ratio of the distribution under the the policy being trained to the reference policy. So the intuition is that if it's bigger changes, it'll weight it more heavily. And then it's going to want to weight it in a direction that is advantageous. But then we also, and I didn't quite understand this min and clip. The way I think of clip is it constrains it to within this value, but somehow we're taking the min of that and then the clip pretty much of the same thing. Oops, that's in the
Yeah,
wrong.
it's just saying that the thing on the left, right? Just the ratio times the advantage.
Oop.
Okay. We're going to use that. And the only time we don't use that, okay, is when clipping it gives you a smaller value. So basically, if that ratio is very large, if that ratio is 17, then instead we're going to use 1.001 instead of 17.
Oh, I see. You're clipping the
Yeah.
ratio.
So
You're
like
clipping
if
the
you,
ratio, basically, not
yeah, I don't,
clipping the advantage. Huh.
right. I don't know what a realistic epsilon is, but if I use 0.01, then you're basically saying that ratio has to be between 0.999
Yep.
and 1.001. And so if it's anything bigger than that, if it's 2, 17, 1.2, we're just going to drop it down to 1.001.
Yep. And then here's the kind of the intuition about it. So we're trying to take the biggest possible improvement step on a policy using the data we currently have without stepping so far that we accidentally cause performance collapse. And that's what these little tricks of adding clipping and these ratios are doing.
Yeah, and we see clipping elsewhere, like there's gradient clipping when you're running
Yep.
gradient descent.
To help
Sometimes you
stabilize,
say early on we might have some very wild, large gradients pointing in the wrong direction. So unfortunately, you don't know at what threshold you should clip it. It's like now you've just introduced a new hyperparameter. Like at what point should I clip it? But nevertheless, that's the general concept, and that's why small batch sizes are bad for really large models. So when you look at them training Llama 3, they're not training it on a batch size of 32. They're training it on some ginormous batch size that's tens of thousands.
Okay. You guys have punishments. I'm going to skip this one. Another concept about RL that is kind of important is this idea of exploration versus exploitation. So if you're trying to figure out the right trajectory, you don't know what all the trajectories are, so you're sampling some. And once you develop a policy that's guiding you down a good path, what you think is the better path, greedy exploration would mean, or exploitation would mean, always pick the best at each state, and you're expecting somehow to end up at the best spot. The greedy epsilon means that, yeah, okay, that's good because you're going to seek out good paths, good rewards. But the epsilon means that occasionally you should take a choice that is suboptimal, because sometimes you may discover a different path that is actually better than the path that you have discovered so far. And so I was trying to capture this. There was a slide that we had back when we talked about this before. I couldn't find that one, but the idea is that there's many different trajectories along here. If red is the, let's say, somehow red is a good one, and blue is not a good one, but it looked like it was good in the beginning. You need to occasionally jump out of that so you can find this other trajectory path. So that's the idea that you'll hear in RL, that exploration versus exploitation. Some of them are just this epsilon. Sometimes I think we saw, is that spelled wrong? I think we saw Bayesian exploration, where you looked at, in this place, when you're uncertain, then you want to explore more. And if you have low uncertainty, then you maybe want to just stick to the path and get on to another place of more uncertainty where you can look for better paths. And there may be other approaches, but those are the two that came to mind. The environment, so I wrote this before I read that initial states space. Sometimes you have systems where you can go to a known state. Sometimes you always have to start at the beginning. I think when you're doing robotics, real life training, they typically always start at a given spot, and you're going to have to get to a state, you have to navigate to there, and you follow those paths along. Okay, anything there? The other concept to keep in mind, I stole this from a different place, so it doesn't exactly say what we want, but is this idea of on policy and off policy. I thought I'd heard it as online, offline, but on policy basically means that every time you're going to do an update, you do it based on data that was collected using the same policy that you're updating. Off policy means that you may have generated the data with a policy that's slightly different, and you're going to reuse it to update your current policy. Again, slightly different than the policy that generated it. The advantage of on policy is that sometimes you can get, especially with that value function, you can think about the trajectory. Depends on the trajectory as to what the value is. Small changes might have a big change on the value function. But the advantage of off policy is that sometimes the forward pass going through the environment takes a substantial amount of time. So if you and energy or whatever. So if you can run experiences through that, in this state, do this action, here's what the result was. If you can record just what's initial state, what's the reward, initial state, action, next state, and reward. If you can record those, then you can learn from that experience playback and not have to actually go back and do a forward pass through the environment. So these are kind of important concepts. Any comments? Okay.
Roger, so is that last bit more of an optimization though, or?
The off policy?
Yeah.
I think if the forward pass through the environment had zero cost, you would always do on policy.
Right. Okay. I see what you're saying. But it is off policy is an optimization to potentially get you there sooner.
With lower cost, right?
Lower cost, yes. Okay.
Yeah. Yeah. So like I used the example of robotics. I've seen videos of, they got a room full of robots going through doing this RL. And each one of those, if you're doing it in a simulation, you can do it pretty fast. If you're doing it in the real life, it's much slower, and the cost of having all those robots is high, et cetera. So in those cases where you're doing it on a physical robot, you gain by trying to record those with a policy that's close to the current, the policy that you're evolving.
Mhm.
Just record them and then play those back multiple times, trying to optimize your policy using pre-recorded data. And you can play variants of it. You can do that and then decide, okay, my policy has moved too much. We need to collect new data. Sometimes they weight it by how much it is different, how much the distributions differ between the two policies. But yeah, that is the optimization.
Okay, thank you.
And this was just out of the OpenAI spinning up just a list of all the different RL methods that they cover and why. I'm not going to go into those links if you want to follow it. There were some videos here. I'm wondering what we should hear. Quick decision. So 7:50. We could play with just watch through some videos and make it end on time today. Or we could keep going and start into the Instruct GPT stuff, the RLHF stuff. Any opinions?
I vote to maybe do an example, or if these videos are short and to the point type thing.
Yeah, relatively short.
Yeah, my guess is you're not going to be able to do much of Instruct GPT in 10 minutes.
Yeah. I mean, it is. Yeah, there's probably too much. Yeah, we're not going to get through that.
Yeah.
And we did do the caveat right at the beginning that might go longer, right? So.
Yeah, well, we know ourselves better than that,
Well done, everybody.
All right. Are you getting the sound on that?
I heard somebody say, "Well done, everybody," but I don't know if that.
Yeah, no, that was me. I didn't hear any sound from the YouTube, though, I don't think.
Okay.
I'm going to play again. Let me know. I think I might have started sharing without any sounds.
No sound.
No.
All right. Let me.
You probably have to share the window rather than the screen if that's what you're doing.
There's these little guys. All right. Did you get that?
Yep.
Okay. So these are just a couple of real quick search on RL. Inverted pendulum is kind of a common one. Again, these are these are back, you're not thinking about complexity of language models and stuff like that. These are very simple ones. They're just where they're developing the reinforcement learning concepts. This is one that would be probably fully observable, probably continuous. And I think
It looks like the Deep Sentinel lab.
the who?
The original Deep Sentinel West
Oh,
Coast machine learning
yeah.
lab.
Yeah.
Oh,
yeah.
up on the second floor?
So these are just examples of them trying to learn. So you see they can't necessarily keep them up. The policy isn't trained. This is during the training of it. And then,
Just to be sure we understand it, the idea is to hold that stick upright, perfectly, right? Perfectly balanced.
right. So that what they can measure, there's something here, angle. I don't know if it's angle and velocity. And what they control is the angle back here. So it's essentially controlling the position of the fixed end of the pendulum. And they're trying to move the fixed end of the pendulum so that the pendulum is vertical. And it's not doing a very good job. You can see it gets it. Okay, I've figured out how to swing it up, but then you'll see I can't keep it up there because the policy is not optimal yet. Oops. I drop it someplace. And then this is an example. It's a different system, but same type of thing, controlling the position of the fixed end of the pendulum and measuring. It's not controlling the twist of this, it's just measuring the angle. Probably as a position, they may provide both angle and velocity to the policy. And now this one knows how to keep it. Looks like it's both keeping it vertical, but it also wants to keep it in the center.
It looks like they have some degrees there on the markings.
Yeah.
Or radians. Because it's trying to return to 0 every time, I guess.
Right. Yeah. It wants to keep it vertical and in the center. So that's fun. What was this other one? Oh, this is just the inverted pendulum starting from straight down. It learned how to get it to move.
That was impressive.
I remember this being harder than I would have expected when we were playing with these.
I remember Shalom once brought the gadget.
Shalom.
The Deep Sentinel lab, and he wrote the code, and the driver for it would send read the signal and train the model, and did exactly that. I mean, it's a well-known problem, but still, he brought the whole device and everything there.
So these are probably ones that have like one action space, which is what angle to put it at down here. And it probably observes at least position in this optical encoder here at the top. So it's a continuous, I would guess it to be a continuous action space and one or two-dimensional continuous observation spaces. And there's one I remember from this that was fun, that was RL related. So that's on the simple.
This is a real B&H customer story.
Okay, we checked all 4 systems and keying was a go.
The B&H
on Earth.
So this is one I remember being a fun one when we were looking back at RNL. So this is going from very simple, low dimension up to much higher dimension and a lot of
The simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in.
That or not, but that was a fun one.
The best was when they locked the entry and they were just holding on to it like very tight.
Yeah.
Pushing the They didn't want the seeker to push it and come inside.
I'd like to know how many rounds it took them to get to that point of, understanding.
They said millions of rounds of training, right? Didn't I hear
they?
that word?
I didn't hear a number, so might have been me.
And I
can believe it's millions.
I don't know what the state space was, if they had like an image or if they had information about the objects and location of objects, etc. But it was just a fun one. I mean, it's gone on to do much bigger things than that. The Alpha Zero that we talked about was reinforcement learning. What's the ones they're using now to play video? Not only play like superhuman video games at superhuman levels. I think they're now making teams of these things that are
Star something, I don't remember, right? There was a game like Star something, Capture the Flag, many of those.
Yeah.
I know they made some Dota bots that were pretty impressive for a while, but I don't remember what they were called.
That might have been the one I was thinking of, yeah. And the part that's really cool, again, we haven't been playing with RL much, but the part I always found cool is this allows the AI to learn stuff that we don't know. It's not supervised. It's going out and figuring out about the environment and learning stuff that we don't know. So it seems really powerful. I know Sally was big on it at the time, but okay. So do we want to go ahead and stop recording then?
I shall
Sherry?
do that.
And then I will